3, 2, 1. Let's go. Okay, so we have set the final stage. So let's get the show on the road. All right. So the goal for today is to learn how to solve homogeneous linear systems of different. Homogeneous linear systems, differential equations. First order differential equations, which, again, remember, we can always rewrite as x prime is equal to ax, and we will focus in today on the case where A is a 2 by 2 matrix. And we know that that means now that we're going to need a fundamental set of solutions that has two linearly independent solution vectors, x1 and x2. And before we get into it, I will note that pretty much everything we talk about today will work for 3x3s, 4x4s, 5x5s, and so on and so forth. But the minutiae there really kind of goes off the deep end, so we're not going to touch it. So we'll focus on 2x2s. I'll point out kind of the spots where this works if it was a 3x3, and this doesn't work when it's a 3x3, and so on and so forth. All right. So it turns out that we can pretty much just jump right into how this is going to go down. Right, because we set some stuff up when we were talking about matrices, and we haven't quite touched them yet since then, and I made a huge deal about them, and said they were the most important thing, not only for what we're talking about, but, like, for humanity, and that's the idea of an eigenvalue and an eigenvector. So, choose a eigenvalue and an associated eigenvector for the matrix A. So again, remember, this means that if I multiply the vector v by A, that is equal to the vector v scaled by lambda. Right, the word eigen we stole from Deutsch, meaning same or similar or self, or, you know, the context dependent on the translation. But in other words, right, the vector and the scalar behave the same in terms of the matrix. So multiplying the vector by the matrix is the same thing as scaling the vector. So, that equation right there, exactly what I just said. Okay, now, what are we going to do with this? Well, note what this does. It takes a vector and converts matrix multiplication into simply scaling the vector. So, if I were to plug in something for x involving the vector v, this multiplication by a would go away. Like, oh, I don't know, if we were to choose x to be e to the lambda t times v, right? Because the derivative of this, right, of course, will spit out a lambda. And, oh, lambda v just happens to be a times v, and this is a scalar, which means I can move it around the matrix multiplication, and, oh, hey, there you go. E to the lambda t times v is a solution vector. So in this case, it is a 2x1 vector that has functions inside of it, the function specifically being scalar multiples of e to the lambda t. So we now have a method of creating solutions. We simply just need to find eigenvalues and eigenvectors. Right, well, how do you find eigenvalues and eigenvectors? Well, you solve a polynomial, meaning that we've got three cases we need to look at, so let's get going with the easy one. Alright, so a 2x2 matrix will produce a characteristic equation that is a second-order quadratic, so two distinct roots, repeated root, or complex ones. So we'll deal with the easiest possibility, which is distinct real eigenvalues. So remember the form of the characteristic equation, we'll subtract lambda off the diagonal, and then take its determinant. Since this is a 2x2, it's always rigged to go in a very certain way. Specifically, the constant term is simply the determinant of the original matrix. The linear term is negative the trace, which is the sum of the diagonals, and lambda squared is positive. Lambda squared, no constants there at all. Okay, so that conveniently gives us lambda squared minus 1, which has two values, as promised, plus and minus 1. So our eigenvalues are plus and minus 1, so as we noted, to form the solutions, we need to then look at e to the t times an associated eigenvector and e to the negative t times an associated eigenvector. So that means for each one of the values, it doesn't matter which eigenvector we get as long as we get an eigenvector. Okay, so let's talk about how we find those again. So for lambda equals 1, that means we look at the equation, the matrix A minus the eigenvalue 1 times the identity matrix times v equaling 0, v being the thing we wish to solve for. So we'll have the entries of v be v1 and v2. We're subtracting 1 times the identity matrix, which means we're subtracting 1 off the diagonal, which gives me this. And from this I can read off an equation. Now, this gives me a relationship between v1 and v2. As we noted, the whole conceit of an eigenvector here is that when you do A minus the eigenvalue times the identity matrix, that matrix fails to be invertible, which means that the matrix equations do not have unique solutions. So when we set this up, we get this equation, so 2 unknowns but only 1 equation, so there's infinitely many answers. Okay, so that means that we've got a lot of choices. To make our lives easy, let's simply plug in a number for one of the values to make our lives as easy as possible. Right, we want to avoid fractions, we want to avoid weirdo things with square roots, things like that. I mean, you could go nuts, you can choose whatever you want here, but let's keep it simple and clean. So I chose v2 to be 1, which then solving for v1 gives me 3. So an associated eigenvector for lambda 1 is 3, 1. Is this the only eigenvector? No, there are infinitely many, but I picked one that I deemed the most appropriate, which was 3, 1. There are others. Any other eigenvector you produce for lambda equals 1 is going to be a scalar multiple of this, of course, excluding choosing one of these to be 0. Because again, remember, the whole conceit here is that this is a non-zero vector, causing this matrix to go non-invertible. So, if you were to tell me your eigenvector was 0, that is the grade you will be receiving for the course. So, alright. So I've got an eigenvector for lambda equals 1, and then I simply just repeat the same process to get an eigenvector for lambda equals -1. Here again we see you should always end up with one equation with 2 unknowns, and so pick something to make life easy. In this case I picked 1. Normally, 1 is almost always like the go-to, just pick 1. Although sometimes you get a little creative where you pick like 4 or something to make the terms divide out. I mean, you're free to choose whatever you want, but have fun with it. But don't go nuts. Don't give me an answer that's like pi and then like 14. But don't do that to me. But anyway, so we now have 2 solutions for our system, but we need to answer a question: are they actually linearly independent? Because again, remember, the whole the idea here is that, well, if we create 2 solutions, we'll superposition to create the general one, but that only works when we're linearly independent. So let's go ahead and check that by setting up the Wronskian, which in this case is, for systems, means just slam these 2 together into a matrix and take its determinant. Oh, hey, it's non-zero. Is that a surprise? No. So, hey, I've got the general solution now. I'll just take these things, scale them up, and add them together. Superposition tells me that's a solution. And now, not only do I know that is a solution, I know that every solution is going to look like this. So we've got our fundamental set of solutions, and that's it. So that's the full story. And this works regardless of the eigenvalues and the eigenvectors. So if you have a 2x2 matrix, you look at your homogeneous system, the matrix has distinct eigenvalues, lambda 1 and lambda 2, then your general solution will just look like this. So it looks virtually identical to what we saw with second order differential equations. Just now, instead of the e to the lambda t, there are now these eigenvectors. So it's going from, because note, the solution here is a vector solution, right? It's not a, here's your function. Well, it's, here's the functions that you need. There's more than one function, right? So, there you go. Alright, that's it. That's the story. And for a quick example, the general solution to this one, so for another one, you can fill in the details that 3 and -1 are the eigenvalues, and 2, 1, and 0, 1 are the appropriate associated eigenvectors. Okay. Alright, so like I said, this these techniques that we're talking about for 2x2 matrices will upscale to higher order ones. So in particular, if you have a 3x3 matrix and you have 3 distinct eigenvalues, then you'll get 3 solutions just by finding the associated vectors. And it works for 4x4 and 5x5 and so on and so forth. So in the distinct case, it is beautiful, it works great, it's wonderful, it's perfect. Not a surprise. Alright, so that means what about the other cases? Alright, well, that's when things get spicy. Okay. So, quite surprisingly, repeated eigenvalues actually have a bit more going on with them than what we had seen before. So in the past, when we had repeated, we applied reduction of order and moved on with our day. Now it turns out that for systems, repeated actually further splits into 2 possibilities. So here's the good version. Okay, now before I even attack this with our matrix methods, let's note something about this equation. If I were to rewrite this in terms of systems, right, because again, we're writing it as matrix notation, this is really the following system. dx dt equals x, and dy dt is equal to y. The system is already decoupled. We can just directly solve this from just our knowledge about how this is supposed to work. X should be c1 e to the t, and y should be c2 e to the t. So that means the matrix method should produce the following solution. x1 should be e to the t, and x2 should be e to the t 0, and x2 should be 0 e to the t. Right. So here, note, I converted my matrix equation over to the actual system, and then I solved it using my known methods, and then reading off this, I was able to rewrite the vector solution. So note, I started with vectors, and I worked my way back to vector answers. Okay. So let's see if that actually happens. Okay, so the characteristic equation is 1 minus lambda squared. Now, note, if I wanted to write it out using the equation that I know, lambda squared minus the trace plus the determinant of the matrix, I could have done it that way, but this one, it's super easy. You just leave it like that, and we find that the only eigenvalue is 1. And the vectors then must satisfy the following. Well, this just tells me that 0 is equal to 0, so v1 and v2 are free to be whatever they want to be. So I choose 2. I make 2 different choices, so v1 is 1 and v2 is 0, v1 is 0 and v2 is 1, and hey, look at that, there you go. 1, 0 is an associated eigenvector for the eigenvalue 1, and 0, 1 is another one. And note that they're linearly independent, pretty easy to check by taking the determinant of, so taking the Wronskian of those 2 solutions, you'll get the determinant is not 0. It'll be a good time. Specifically, you'll get the determinant is e to the 2t. So, yeah. Alright, well, that just went perfectly. Yeah, it was blip, done, didn't have to do anything. Alright, well, there was something special about this particular case here, right? Like I said, it's the good one. Everything's fine. The reason everything was fine is because my variables were free. Both of them were free to be whatever I want, and since I had both variables free, I was able to create 2 linearly independent vectors. So we got to get into some matrix deep lore here for a moment. So the algebraic multiplicity of an eigenvalue is the number of times it appears as a root. So for example, the one we just looked at has an algebraic multiplicity of 2, because the lambda minus 1 term, or in this case 1 minus lambda, doesn't matter, the order here, because we're going to square it, right, is squared. 2 of those terms appear. So lambda equals 1 has appeared as a root technically twice. Even though it only has 1 root, the root appeared twice because it's being squared. The geometric multiplicity is the number of linearly independent vectors that can be formed. Okay, so this one that we just saw has a geometric multiplicity of 2, because even though I only technically had 1 value, I could create 2 linearly independent vectors. Okay, so what is known to be true is the following. The geometric multiplicity never exceeds the algebraic. So if you have a multiplicity of 2, your geometric multiplicity could be 2. It also could be 1. If your algebraic multiplicity is 1, though, note that forces the geometric to be 1, so that's somewhat nice. It's worth noting, this is, so a lot of times, so in these, lower level math classes, we kind of just get presented facts and we get told, like, yeah, this is true, and then you're like, alright, it seems legit, and then, you work on it. And if you take some higher up math courses, you go a little further in your math life, right, you have to actually prove that these claims that you've made are true. And I am not shy in telling you that if you were to ask me to prove this right now, I would have absolutely no idea what to do. I have never seen a proof of this, to be honest, because in my graduate level course where we were talking about matrix theory, the professor just wrote this on the board and said, yeah, I'm not proving this, but it's true. And he basically said, like, yeah, the proof is whatever, it's not interesting. But anyway, so this and Stokes' theorem are the two things that, so if you're taking Calc 3, you know what Stokes' theorem is. Those are the two things in all of Calc 1, 2, 3, and DiffyQ. Those are the two things that I have no idea how to prove. I just know they're true. Stokes' theorem is, like, nasty to prove, if I remember. I was talking to a seasoned professor in the department, and he just outright said, like, yeah, I've never seen a proof of it. Who knows? They just tell me it's true. So, if you ever feel like your math professors might be lying to you about something, it's a good chance. They're like, well, somebody told me it's true, and I believe them, so. Okay. So, like I noted, when they're equal, there's no problem, right? Because I want two linearly independent solutions, so if I have two linearly independent eigenvectors, I can make the solutions and move on. But, well, obviously something can go wrong. Alright, well, let's set everything up here. Okay, so again, we find that the only eigenvalue is lambda is equal to 1, so the algebraic multiplicity here is 2. But now when I go to find the eigenvectors, I find that, well, only one variable is free, v1 specifically. So we can only create one eigenvector. So that means the geometric multiplicity here is strictly less than the algebraic. So here's an example of the strict inequality. In this case, the eigenvalue is actually called defective, which is... Some of the names we pick to describe things, math objects, are great. There's like defective and normal and abnormal objects. It's great. Anyway, so what does this mean for us? Well, that means we're only able to create one solution, right? I only have one eigenvector that I could ever make, so I only can make one solution. But I know I have two solutions, so how do I get the second one? Well, before, what would we do? Well, we went, hey, reduction of order, right? Yeah, let's do that. You sort of do that here, but it's nowhere near what you would think it would be. So in the past, reduction of order just ended up being, well, you multiply it by something, or it's this something times another function. The second solution, in this case, ends up being a lot more involved. So we see the multiply it by t making another appearance, just, slap it with this function. But now this other term shows up, where this p here is different from v. This p specifically needs to satisfy the following equation. So where v, the eigenvalue, satisfied a minus lambda I v is equal to 0, this p vector satisfies a minus lambda I times p equaling v. P here is actually something called a generalized eigenvector. And speaking of deep lore, this is related to a very famous theorem called the Cayley-Hamilton theorem, which says that matrices have to satisfy the characteristic equation. That was something that we actually did take the time to prove, and that is also not an easy proof. And that is also, that proof's involved. That proof's actually not too bad. There's a sneaky way of proving it. But it's like you had to, so the class that I took was about matrix theory, and then I was also taking a class on functional analysis, which if you've read the little instructor bio, is my branch of mathematics, and as I noted, it's linear algebra combined with calculus, so you're taking matrices and you're taking limits, basically. And it turns out that in my functional class, we learned some little tricks. So we were proving the Cayley-Hamilton theorem. I was like, oh wait, I think you can just do this thing with the spectral theorem. And then my professor was like, yeah, but we didn't prove that yet. So, anyway. So, yeah, so it turns out that this is what you need. This here is the other solution. The way of deriving this is very similar to the way you would derive, the reduction of order method, but I'm not going to get into it. But basically, this is how it pops out, and it'll end up working. And hopefully you can see that multiplying everything by a. You can kind of hopefully see why this ends up working, but anyway, let's actually work out the deets on this. So for an example, we have this one here. We have an eigenvalue of 1. We have an associated eigenvector of 1, 0. So my first solution is nice and easy, e to the t times 1, 0. My second solution, I need to find p. So now I set up a minus the eigenvalue, which is 1, times the identity matrix, times p, and then I set that equal to my original eigenvector. So I set it up like this, and then here we end up with one of the variables is fixed, p2. Note that it's equal to 1. p1, and now here's where you finally get to do what you want to do. p1 is free. p1 can be anything. Make your life easy and pick it equal to 0. Right, so you are allowed to here because p is not an eigenvector. It's a generalized one, so you get to cheat a little bit and finally get to plug in 0, so that's nice. Alright, so now that we've got what p is equal to, we can form the other solution, where you do the thing we normally do, which is multiply by t. And now we take e to the t and multiply it by p, which in this case is 0, 1, and that gives me my second solution, and there we go, we have now created the general solution. Okay. So here we saw for repeated eigenvalues, in the case where we can't create enough eigenvectors, we have to bring in this other tool here to solve it, where we use these things called generalized eigenvectors, and this term here, which almost looks like exactly what we did before, multiply by t, but there's this extra term that just unfortunately needs to be there. Okay, and the book goes into a little bit more detail about it. I didn't want to bury you with that because I'm going to bury you with the complex stuff in a moment here. So, but if you're interested, go in and read it. But basically, the punchline is as follows: if you have a repeated eigenvalue, two possibilities. If you have enough eigenvectors, it comes out great. If you don't, it's still not too bad. You just got to do another calculation. Okay, and here I cleaned it up a little bit. And here in this form, you can kind of look at it and see, kind of like, hey, this is a constant term, and then here's a first order term, right? It's a p and v are constants. Right, even though their vectors are only full of numbers. So you can kind of maybe see like, ooh, I bet if we were to go to a 3 by 3, there might be like a t squared that shows up or something. And it's worth noting that for 3 by 3 matrices and repeated values, things can go completely bonkers. Your book, basically, totally sidesteps and it goes like, if you want, basically. There's another way of attacking this stuff using what's called the exponent of a matrix. And there is a section in your textbook about it. We unfortunately are not going to get to it. If you're interested, check it out. Basically, so speaking about what I was talking about with functional analysis, where you're taking limits involving matrices, another thing you can do, if we can take limits, is we can make series of matrices. And yeah, that's the stuff, let me tell you. So to create the exponent of the matrix is actually the series, and it's oh boy, it's some spicy material. But anyway, so for us, that's the story, and that's all we're going to do. Again, we're not going to go beyond 2 by 2s. I will note that for 3 by 3s and beyond, this gets especially fun. All right, well, that leaves us with one final case, and that's the case of complex eigenvalues. Yeah. So, hey, here's a pretty innocuous-looking equation. This doesn't look that bad. Characteristic equation is this. There are the eigenvalues, -1, plus and minus I. So, before we begin finding eigenvectors, let's make a plan of attack. Okay. So, If you've got a complex eigenvalue, alpha plus I beta, then an associated vector is going to be complex. It's going to involve complex numbers, which means we're going to be able to pull it apart as A plus IB, where A and B, the entries of those are real numbers. Okay. So, by Euler's formula, we know that e to the lambda t then would look like that. And like I said, I was going to bury you here. I didn't bury you with the repeated one. I went a little easy on you here. But here, this sprawls out very quickly. So if we then look at e to the lambda t, lambda 1t times v1, plug everything in and pull it apart so we get a term that only involves real things, and a term that only involves real things but real things times I, we get this. And as we have experienced in the past, well, the real part and the imaginary part, these are probably going to be the solutions, but we got to make sure that's what's going to happen. And how are we going to do that? Well, we'll superposition that, right? The other eigenvalue is alpha minus I beta, so that means the vector has to look almost the same, or instead of a plus, there's a minus, right? It's the conjugate. The same is true here. So that means when I set up the e to the lambda t times the v, I get this, which is identical to what we had before, but instead we have a minus sign instead of a plus sign, right? We get the conjugate. Okay, and that means by superposition, if I scale and add them and I choose my scalars correctly, I can isolate the real part, which is that term right there, and I can isolate the imaginary part, that term right there. And there we go. We can then get two solutions, and I'm not going to go through the details, but they are linearly independent. Go ahead and set up the Wronskian for that one. Have fun. Okay, so now that we planned the work, let's work the plan. Okay, so let's go back to this matrix, -1, 2, -1, -3. As noted, the eigenvalues here are -2 plus or minus I. So that means we only need one eigenvector, right? Remember, we just need to find A plus IB for -2 plus I. Okay, and I want to stress something here. There are technically two, -2 plus I and -2 minus I. Always go with the plus. If you go with the minus, you need your v to be minus then. And that just ends up complicating things, so do not do that. Alright, so we're going with the plus. So subtract this off the diagonal. That gives us this. Okay. Now, this gives us two equations, it seems. Now, note the top equation is this. So if I were to look at this times that, plus this times that, right, do the matrix multiplication. I'll just go ahead and make my life as easy as humanly possible and choose v1 equaling 2, because then I can divide out the 2 here. That's right. So like I said, usually we pick 1 or 1 for the sorts of things, but sometimes we'll pick a number to make it scale out nicely. In this case, I picked 2. So that means that v2 has to be -1 plus I. So v then I can pull apart into 2 -1 plus I times 0, 1, like that. And here I am very happy with this conclusion that I've got. Oh, excuse me. Sorry for burping. Anyway, so we now know what A is and we know what B is, so we can now solve. Because now x1 is e to the alpha t, cosine beta t, beta is 1 in this case, put in A minus sine beta t times B, which I can clean up as best I can as follows. And then x2, I can then do that, clean that up as best I can and get that. And therefore, we then get that as our general solution. Scale those by C1 and C2. Right, note the A and the B swap, and it goes from negative to positive. And that's just how the algebra works out. I don't really have any sort of other ingenious explanation other than, well, it's just how it shakes out when you plug it in and apply Euler's formula. All right, and that's pretty much it. That's the story. So if you've got a 2x2 matrix for your homogeneous system, you've got complex eigenvalues alpha plus or minus I beta, then the solutions will look like this, where you look at a eigenvector associated with alpha plus I beta, where v is equal to a plus ib. That's it. So for another example, similar to the one we just did, if we look at 1, 1, negative 2, 3, in this case, the solutions will end up being that, so you can verify that the eigenvalues are 2 plus or minus I, and the vector is 1, 2 plus I times negative 1, 0. So work out the details on this one on your own and make sure to include the minus sign right there. But that's pretty much it. Now, when you go to a 3x3 and above, things get dicey because you can have complex eigenvalues repeat, and that's when stuff really starts going off the deep end. So we're just go wash our hands, walk away, go like 2x2 is good enough for us. So, because we got one more thing we gotta do. We now know how to solve the homogeneous ones. How do we solve the non-homogeneous ones? And as we're going to see, it's going to be very similar to what we did before, but kind of what we saw today, a little bit more ins and outs and what have yous than we had before. So, hope you enjoyed this penultimate video. I'll see you one last time next time.